rather noisy upstairs neighbour. Alright, so the fourth example of applications of perturbation theory. So we're talking about the helium atom. So talking about some of the earlier, in the previous session, talking about a bit of the theory. So helium atom, okay, the second smallest atom, element with 2 protons in the nucleus and two neutrons. In fact, a helium nucleus is often referred to as an alpha particle. So 2 electrons. Electrons are fermions, therefore the wave function of this multi-particle, in other words 2-particle system, has to be antisymmetric because fermion wave functions have antisymmetric wave functions. Done that from earlier. Now, how does the perturbation theory, what is the perturbing Hamiltonian? What is your H dashed in this case? Well, it's the interaction, the disturbing Hamiltonian, if you like, perturbing Hamiltonian, is due to the interaction, the repulsion between the electrons, the 2 electrons. That's your perturber. That's your H dashed. The potential energy due to the repulsion, the electrostatic repulsion between the 2 electrons, right? Okay. Now, if there were no, if there's no electron-electron interaction, so if you switched off their charges in a sense, if there were no electron-electron repulsion, then the wave functions of these individual electrons, you assume, would be hydrogen-like, right? Because the electron would just feel the attraction of the protons in the nucleus, and those 2 electrons in the helium atom would feel that and feel no interaction between themselves, between those 2 electrons. Okay, so the wave function then for each electron should be hydrogen-like. So your U0 would be of the same form as hydrogen, but with one difference. We're now talking 2 electrons, so we're talking a 2-particle system, and therefore the wave function, hydrogen-like, but must be antisymmetric. Okay, so we need to first form these hydrogen-like antisymmetric wave functions. So how to do that? Well, now in the unperturbed state, before you have your H dashed, before you switch on the interaction between the 2 electrons, your wave functions will be of this sort of form. In other words, a spatial part and a spin part. Okay, we just product them as usual. These are amplitudes. We just take the product of them. The basic assumption in quantum mechanics, multi-particle systems. Right? So, a pre-perturbed or unperturbed state for 2 particles of this form. So a spatial part and a spin part. Okay. So U1 R1, U2 R2, particle 1 spin up, its component, z-axis component, up and down, spin up, spin down, right? Now that's just one form. Now we can swap the positions of the 2 particles, right? We could have for the U's. Now, and remember the Pauli exclusion principle says you cannot have two particles in the same system with identical quantum numbers. Now, we could have 2 spin-ups, but these would be different. The spatial parts would be different. That's okay. That's compatible with the Pauli exclusion principle. But we have 2 spin-downs. In fact, let's see. So the text is saying you've got 8 combinations. Now, does that make sense? Eight of them. So you could have 1, 1, 2, 2, and then you could have both up, both down, up, down, down, up. There's 4. And then swapped. You know, R2, R1. So it doubles everything, so 8, I guess. Alright, okay. So 8 combinations of this kind of thing, alright? And you can combine them. You know, we talked about half a course ago when we were talking about multi-particle systems, identical particle systems. So you can combine these 8 in 4 ways to generate anti-symmetric wave functions. Okay? Maybe do that as homework. And generate. Well, you can almost just see from from inspection, just looking at it. So here they are. So there's 1, 2, 3, 4. Four possible anti-symmetric wave functions, and these. See the bigger picture. What are these for? They are anti-symmetric wave functions, hydrogen-like. Now these are from solutions to the hydrogen atom. So they're hydrogen-like before the perturbing interaction is switched on, in a sense, before the interaction between the 2 electrons is switched on. So these, in a sense, are anti-symmetric, unperturbed wave functions. Okay, these 4. Right? Now, can you see that they're anti-symmetric? Swap the R1, R2, you get minus. So if R1 and R2 become the same, then well, if R1 and R2 are the same, this becomes 0, this becomes 0, this becomes 0, this doesn't. But if all the quantum numbers are the same, but this does, this becomes 0. So in all 4 cases, your wave function becomes 0. That's pretty well required by the Pauli exclusion principle. Right? You cannot put 2 particles in the same system having identical quantum numbers, having the same state. Not allowed. Right? That's actually, if you do advanced quantum field theory, probably 2nd year masters, if you're following me to that level, we will actually derive there's something called the spin statistics theorem. It's a famous theorem in quantum field theory, where the Pauli exclusion principle is actually derived. It's a consequence of principles used in quantum field theory, QFT. So you can actually derive it. Right? It's not just thrown at you. It's well, Pauli intuitively, he was wondering why the atoms had, in the periodic table, in the Mendeleev table, why were atoms, why didn't all the electrons in an atom collapse to the lowest energy state? And in that case, why do atoms have structure? Why are there many dozens of atoms? Why is that? And he eventually dreamt up this exclusion principle to account for that. But later, several decades later, I think, this famous spin statistics theorem was discovered. Spin statistics. What's that? Well, we mentioned this before. Like fermions have half-integral spins, and bosons have integral spins. And the bosons, in practice, they're the particles that cause force interactions. By exchanging bosons, fermions feel a force. And the fermions, they're the sort of stuff particles. They make up the matter of stuff. And so you can think of fermions being the substance and the bosons being the force carriers between the fermions. Due to the exchange of bosons between fermions, the fermions feel force. Put it that way. Right? So fermions have half-integral spin and the bosons have integral spin. And the statistics, how does that come in? Well, fermions obey Fermi-Dirac statistics. That comes out of statistical mechanics. I'll probably give a course on that as well. And bosons, they obey Bose-Einstein statistics, a different kind of statistics. And the spin statistics theorem shows why certain kinds of particles, in other words fermions or bosons, have certain kinds of statistics depending on their spin. Right? And the theorem shows that particles of a certain kind of spin have a certain kind of statistics. In other words, for example, fermions have a Fermi-Dirac statistics and bosons have a